Okay, so last time we were in, well, we finished up the section on Lie derivatives. And I remember at the end of the lecture, I was getting the feeling that maybe not everybody was following the calculation that I was doing. So hopefully you're all on the same page as me with respect to the geometric construction that led us to that notion of Lie derivative, the thing that is supposed to be a proper tensorial way of taking derivatives in a curved manifold without introducing a connection. Maybe you got lost in the derivation of this result here, where we turned the geometric picture into something that can correspond to a computation. Regardless, hopefully you had time to reflect on this, or you will take the time to do that. But anyway, we'll move on from here, and we'll just basically accept this as, I wouldn't want to consider that to be a definition of the Lie derivative for a vector, because, it doesn't look like much. The geometric construction, I think, is much better suited to give a definition. But nevertheless, we could regard this as a starting point. You could, consider this to be a definition, and then an extension of the definition that would be given to us by the Leibniz rule. And what is supposed to be very remarkable about this, and that's the point that I was emphasizing, is the fact that we can define all of those Lie derivatives by using the partial derivative operator, which is not properly tensorial. So each term here in those equations is not defining a proper tensor, but the guarantee and the consequence of the geometric construction is that, in fact, the combination of all of those terms will give rise to a proper tensor. So the Lie derivative of a tensor is a tensor. The geometric construction guarantees this. And one way to verify this would be to convert all of those partial derivatives into covariant derivatives. You could do that by introducing all the compensating gamma terms. And you would find in all cases, I guarantee you, that in all cases the gammas would go out. So the magic here is that you could replace all of those partial derivative operators by covariant derivatives, and the equation would look identical. There would be no extra terms. All the gamma terms would cancel out. And that would make the point in a different way that, the Lie derivative of a tensor is properly defined as a tensor, but it would sort of, remove the other point, which was, or it would sort of obscure the other point, which was that it can be defined without a connection. So the point is that, none of this here required a connection, and still we're dealing with perfectly well valid tensors. Okay, and then at the end of the lecture, well, came the question, why do we care? Why do we want the Lie derivative? And that's what I'll get into now, and that's going to lead us into the notion of a Lie derivative, killing vector. And that's a good thing, because it allows, so it's the kind of construction that allows us to express a symmetry of a space-time, and then we can use that symmetry to give us conserved quantities. So that's where the, notion of a Lie derivative becomes directly used. All right, so let's put that in the bank for now. We'll come back to this. And let's talk about symmetry and things like this. So I'm talking here about killing vectors. All right, so here I could be talking about any old tensor, and I could be expressing the idea that this tensor would be symmetric under a certain change that we want to introduce in the spacetime. But because the metric tends to play a central role in what we do here, I'll talk about the metric. So what I'm going to say first is that suppose that we have a coordinate system. And, I could call them all sorts of different ways, but I'll call them T, X, Y, and Z. They don't have to be Cartesian. Those are just names. I would suppose that, we are dealing with a spacetime for which the metric happens to be independent of at least one of those coordinates. So in that coordinate system, we would find, for example, that the metric turns out to be independent of one of those coordinates, and I'll pick Y, because why not? So that would express a very important fact, that the metric and the spacetime, more generally speaking, is invariant under a flow or a translation in the y direction. So we have this translational symmetry corresponding to a translation in the y direction. So the metric would be invariant under that kind of transformation where we move everything up in the y direction. So y could be a linear coordinate, then we would be talking about translations. It could be an angular coordinate, we would be talking about a rotation. So the idea is that we have in some coordinates the notion that the metric is invariant under at least one of the coordinates. And clearly that would be an important property of the space-time, and we want to make sure that we can describe this in the most meaningful way and take advantage of that property when we do calculations in that space-time. So practical example, the Schwarzschild metric is invariant under a time translation, and we make use of this all the time when we talk about geodesics. We use the invariance on the time translation to construct a conserved quantity that we call the energy, and that allows us to solve the geodesic equations in a very direct way. So anyway, any invariant property like this is very important, but the idea is that, well, we don't want to rely on coordinates to make the statement about something so fundamental as a symmetry property of the space-time. We want to turn that statement from a coordinate-based statement into something much more geometrical. And the key to do this is the Lie derivative. So that's what I want to talk about here. So we have this invariant property, and I'll just describe, that flow in the y direction as a set of curves like this that we would have in the space-time. So that would represent basically the y-axis. And the idea is that the metric evaluated here versus the metric evaluated here, there would be no difference. So that's what invariance under a translation in y means, although moving across in that direction certainly could introduce some changes in the metric. Here I'm talking about the fact that as we go up in the y direction, nothing changes when we look at the metric. So that's what y-independent means. And if I want to express this geometrically, it seems like a good idea to introduce the tangent vector to those curves. Here I'm drawing the curves to be straight, but in reality, for example, those could be if we're talking about invariance under rotation, those could be curved that are curved. Namely, there would be circles that go around the central axis. So anyway, so the fact that the curves here are straight is not meant to be, deep, or it's not meant to be, a good reflection of what always happens. But the point is that I wanted to introduce curves along which we have the invariance, and then having the curves, we can introduce a tangent vector to those curves. And that vector will turn out to be our killing vector. Killing vector means we have that direction of symmetry. So we have a bunch of curves like this, and we have tangent vectors to those curves, and then the curves become the integral curves of that vector. And in that view of things, geometrical view of things, the vector turns out to be of central importance. The integral curves are sort of, coming in association with it. As we saw, we always have a one-to-one association between vectors and their integral curves. All right, so in that coordinate system, oh, by the way, that's my notation for an equality that holds in one very specific coordinate system, not a tensorial equality. So I'll use that here when I'm specializing the coordinate system in a very essential way. Okay, so in that coordinate system, the tangent vector to those curves in that ordering that I give here, well, it's going to be a vector that has a y component and nothing else. And being tangent to curves along which y is running, y is the parameter, so the tangent vector is going to be a vector that has a y component that's equal to 1. So in that coordinate system, we have this sort of arrangement. And what I want to do now is to turn those coordinate statements into something that will involve the Lie derivative, and the reason why it has to be the Lie derivative, I think you'll see in just a moment. So, given the vector, given the metric, let's look at what its Lie derivative would be in that coordinate system. So the general equality here is just the one that follows, from the general rule here that would apply to any tensor. So first we would take a derivative in the direction of the vector c. So that would be the first term. And then we would have the additional terms, where we have the metric, and here I have to be careful with my indices. So we would have the repeated index here. The second index would be nu. We would have the derivative index that would be coming from the metric, and then we would have the vector. And then we have another term like this, where we just replace the indices as needed. So that would be the general expression for the Lie derivative in any coordinate system. But in this specific coordinate system, while we have all sorts of things happening, first of all, that term over here, well, that with this component here with the for the vector c, that really means the derivative of the metric in the direction of the y coordinate, and that's something we've decided was 0. So in that coordinate system, the first term is 0. And in that coordinate system, that vector has a constant component, namely 1. So all of the derivatives of that vector would also be 0. So in that coordinate system, we get 0 for all the terms. And the conclusion here is that, well, in that coordinate system, we evaluate the Lie derivative of the metric in the direction of the xi vector to be 0. But that's a tensorial equation. So a tensor that's equal to 0 in one coordinate system is guaranteed to be 0 in all coordinate systems. That's one of the fundamental properties of tensors. So if it's true in that specialized coordinate system, it's got to be true in all coordinate systems. So the big conclusion here is that what we have is a statement that says that in any coordinate system, so now it's no longer a statement that we make with the help of a very specific coordinate system. In all coordinate systems, we can say that the Lie derivative of the metric with respect to that vector field that we defined, the vector field is there whether or not we use the y coordinate to describe it. The vector field will be the same regardless of how we choose to describe it in terms of coordinates. We have the vanishing of the Lie derivative in all coordinate systems. So this works in all coordinates. So what we managed to do here is to turn a statement that was very specific to a coordinate system, invariant with respect to a y coordinate, into something that is a geometrical statement of the same thought, but now an equation that can be formulated in any coordinate system. So we've turned that into something much more geometrically meaningful that doesn't rely so much on a very specific system of coordinates. So that's why we wanted, that's why we need the Lie derivative in physics, because it really embodies this notion that a tensor can be invariant under a flow described by a vector field. That's what you get when the Lie derivative vanishes. And in particular, when it's the metric that has a vanishing Lie derivative, the corresponding vector is called a killing vector. That's what it means. When we have an invariance of the metric that can be formulated in this way, then that vector by definition is a killing vector. Killing was somebody who had a very unfortunate name, and that's why we still call it that. All right, so that's the idea. That's why we need the Lie derivative, because it's the Lie derivative that really captures this invariance under a flow. And if you were to compare this, for example, with, if you made an attempt to formulate a statement like this in terms of the covariant derivative of the metric, well, it would be automatically 0. So the covariant derivative of the metric in any direction is guaranteed to be 0 because the connection is metric compatible, as we talked about last time. So the invariance, the vanishing of the covariant derivative of the metric in any particular direction is completely, devoid of any information. So the Lie derivative is the thing that we need if we want to capture the invariance of the metric and the invariance of the spacetime under a symmetry of that kind. So I hope that answers the question of why we would care about the Lie derivative. It's because it's really the the structure that we can exploit when we work on a curved manifold to describe the invariance under a flow. Okay, so I can write it like this. Any questions before I move on to the next step? All right, so I can write it like this, or I can write it in a different way. And that gives us a differential equation for a vector that will tell us whether or not it's a killing vector. So I'll go back up. Let's see how to do it. Yeah, I'll use this board here. So the Lie derivative of the metric, so if we're dealing with a killing vector, we know that the Lie derivative of the metric is going to be 0, and that's a geometrical statement that can be formulated in any coordinate system. But now I'll write the Lie derivative, purposely in terms of covariant derivatives, because I want to reformulate the equation in a different way. So as promised, what I can do here is to rewrite this equation over here and replace all the partial operators by covariant derivative operators. And all the gammas are guaranteed to cancel out, so I'll just write it like that. So the first term would be involving the covariant derivative of the metric, and that's guaranteed to vanish. Then we would have the metric gamma beta, and we would have the covariant derivative of our killing vector. And then we would have the metric G alpha gamma, and then the covariant derivative of our killing vector. So that's a completely equivalent way of writing the statement that the Lie derivative of the metric vanishes, but now we reintroduce the connection. This is guaranteed to vanish because the connection is metric compatible. And because the connection is metric compatible, what I can do here is to throw the metric inside the derivative operator. We can always do that freely when we deal with a connection that's metric compatible. So I'll write it like this. And what this means is that what I choose to do here is to lower the index on the xi vector before I take the covariant derivative. And I'll write it like that in just a second. And here I'll do exactly the same. I'll throw the metric inside the derivative because the covariant derivative of the metric is always 0. And what do I have at this stage? Well, I can actually do this index lowering. And what I find is that the equation can be rewritten as something that will look like a system of differential equations for the killing vector. And that's the equation you would go and solve if you wanted to find, given a spacetime, all the killing vectors that might be associated with that spacetime. You could formulate this as a system of differential equations given the metric, and you would go and try to find all the solutions to those equations. And if you're lucky, you'll find one killing vector. If you're even more lucky, you'll find 2. If you're really, really lucky, you'll find 10 in a 4-dimensional spacetime, but you'll never be more lucky than this. 10 is the maximum number you could ever find. So that's known as Killing's equations. And the way to understand it is to simply recognize that, well, that's a system of partial differential equations for the killing vector, and you can verify that a given killing vector will satisfy this. That's, guaranteed. But more importantly, for mathematical relativity, if you start with a metric and you want to hunt for all the killing vectors, well, the idea would be to write down this equation in whatever metric you happen to be working with. And you would go and try and find all the solutions, and then the number of solutions that you can find that are all distinct from one another would be, all the killing vectors associated with that spacetime. So that's the idea. That's an equation that we'll re-encounter quite frequently in the course. So you want to, make sure you keep it in your memory banks for the time being. And another way to make the statement of this equation is to say that if I take the symmetrized gradient of the killing vector, we're going to get 0. And another statement of this is to say that the gradient of the killing vector is an antisymmetric spacetime. It is an antisymmetric, is antisymmetric. I'll just write it like this. Because, you know, the symmetrized version of it vanishes. That guarantees that the gradient must be an antisymmetric tensor. Okay, so all of that is the math. We might look at, you know, a couple of examples just to see how that, that works. So if we look at the Minkowski metric, that's, you know, clearly the simplest metric we can imagine. So just a bunch of ones or minus ones. So clearly that's a metric that doesn't depend on anything. So we can already identify 4 killing vectors. So sometimes the coordinate system gives you an immediate identification of the killing vectors. Here we have invariance, you know, with respect to t. So the, you know, vector that points in the direction of t is going to be a killing vector. Same with x, same with y, same with z. So we already have 4 translational killing vectors. And those we can we can spot right away, so no need to calculate anything. And beyond that, well, there's actually more. And in fact, that's an example where we can find a maximum of 10 killing vectors for that spacetime. And it just means that the remaining 6 are not so easy to spot, and we can't, you know, really necessarily find them directly from the metric, but, you know, I think you know about them. We have 3 rotational killing vectors, and that's just a statement that if you take this coordinate system and you rotate it in any direction, and you know, there are 3 rotational angles you can introduce to do that, you'll still get a metric of exactly the same form. So that's an invariance of the metric under rotations, and that's, you know, also a property of the spacetime in this case. That's also a symmetry of the spacetime. So that corresponds to killing vectors. I won't write them down because I forget what they are, but they correspond to, you know, an operation of rotation in any, you know, any direction. And then the other thing that we can do is to introduce Lorentz transformations in any direction. So we have 3 boost symmetries that correspond to another 3 killing vectors, and that gives us a grand total of 10, which, as I said, is the maximum we can find in any spacetime. So all of those, you know, symmetries of Minkowski spacetime are very important. They give rise to the Poincaré group of, you know, of quantum field theory, for example, or, you know, just standard mechanics, and they're each associated with killing vectors, and the killing vectors are really the, you know, the mediator of that symmetry. So it's a very important concept, and something that, you know, the first step that we typically take when we want to study a spacetime is to identify all the killing vectors, and we try to, you know, to get that out of the way before we do anything else. Another example would be a spacetime that possesses spherical symmetry, and also I'll take it to be static. So if I write a metric where we would have some coefficient in front of dt squared, some coefficient in front of dr squared, and then the usual thing that involves the angular coordinates. So that describes a spacetime that's spherically symmetric because the metric components here don't depend on the angles and don't depend on time. So it's static and spherically symmetric. And that's the appropriate combination that describes the metric on the surface of a sphere. So, you know, staring at this, we recognize that we have all of those symmetries present. And those symmetries, well, correspond to killing vectors. So let me write them down. So there's one that, of course, corresponds to a time translation. So that's the vector that points in the time direction. So none of the metric coefficients here depend on time. That's what we mean by having a static metric. And geometrically speaking, that means that we have a killing vector that points in a time-like direction. We also have an invariance, and that's explicit. We can spot it right away in the metric. None of the metric components depend on phi. So that's an axisymmetry. Means that we can rotate around the symmetry axis at will. So that's an invariance on the rotations. And we have a killing vector that corresponds to this with an entry in the phi direction. But we have more than just axisymmetry because we can rotate in all directions. So that gives us two other killing vectors. And I'll just write them down. And in the homework assignment, I'm asking you to prove that those are killing vectors. So those point in the angular direction. So we have sine phi and then cotan theta cosine phi. That's in the phi component. And then we have another one where we have minus cosine phi cotan theta sine phi. So if we only had this vector, we would have axisymmetry. But because we have more than just axisymmetry, because we have the full spherical symmetry, we have just, we have three killing vectors that reflect this invariance on their rotations in any direction. So the point I wanted to make here is that those two are obvious because you stare at the metric, we see that it doesn't depend on time, we see that it doesn't depend on phi. That gives us an identification of two obvious killing vectors. Those two, well, they're not so obvious. I mean, I know what they are because I looked it up at some point, and I'm sure I verified it by, plugging that into Killing's equation and making sure that they are killing vectors. And I know that they have to be there because of the full spherical symmetry. But, to recognize that they're given specifically by this is not so obvious, and that's why you have to have those differential equations. That's how you prove that those are killing vectors, by making sure that in the metric that's specified here, the killing equation is satisfied. And, I basically told you how to do the homework assignment, at least a problem. Okay. Any questions about any of this? Yep.
Not normalized?
No. They're very rarely normalized. They would be normalized in, some of them would be normalized in Minkowski spacetime, but typically they're not normalized. Yeah. And in fact, their norm tends to, be meaningful. So they tend to play a meaningful role in the description of the spacetime. In Schwarzschild, for example, the norm of the time-like killing vector would give us the redshift factor between, a point deep in the spacetime versus a point at infinity, for example. So yeah, so the short answer is that no, they're not normalized. Other questions? Okay, good. So very important concept, and that is a very important equation that will come back, so bear that in mind. Okay, so that takes us out of the Lie derivative world for a bit. What I want to talk about now are geodesics. And I want to formally introduce geodesics because we will be playing with geodesics quite a bit in this course. Of course, you know what they are, but I want to reintroduce them in the way that I like to see them introduced. There are different notions of geodesics that you can introduce on a curved manifold. One would be, if you're given a curve, and if that curve has a tangent vector, and if that tangent vector happens to be parallel transported as you move on the curve, then by definition, that curve is a geodesic. And that notion of geodesic is, directly dependent on your definition of the connection. If you play with different connections in different manifolds, you will introduce a notion of geodesic that will be different depending on the choice of connection. So, of course, here we would choose the Christoffel connection. So we would choose to describe our geodesics this way, but it turns out there's a more fundamental property of geodesics that's relevant for, what we do in GR, and that's the fact that they produce an extremum of the space-time interval along any point on the curve. So that's the point of view that I want to introduce, and that's basically the notion that geodesics are path of shortest length, if we're talking about space-like geodesics, or path of maximum length, if we're talking about time-like geodesics. That's what geodesics are in a curved space-time, and that notion matches the connection notion if we use the Christoffel connection. So don't worry about all of this. I just wanted to introduce this, variety of different ways you can talk about geodesics on a curved manifold, but here I'll take the extremum point of view. So what's a geodesic? I would have to use different words whether I'm talking about space-like or time-like geodesics. We're going to be more interested in time-like geodesics here because those would be, the path of free-falling observers. So I'll just use the terminology that's proper to time-like geodesics. So I'm going to draw a time-like geodesic, or at least a time-like curve between 2 points P and Q. And I will say that that curve is going to be a geodesic provided that it maximizes, or at least extremizes, let's use a neutral word, extremizes proper time on that curve. So a time-like geodesic extremizes proper time between 2 points. And I would say 2 neighboring points because all sorts of things can happen if you allow the extension between P and Q, or the distance between P and Q, to be too large. There are all sorts of little, funny technical things that can happen where the extremum property can be lost along the way. But if you take 2 points like this that are not too far off from one another, then it's guaranteed that a time-like geodesic between those 2 points is going to be an extremum of proper time, and in fact, it's going to be a maximum of proper time. So we're not looking for a minimum, we're looking for a maximum. And if you are puzzled about this, well, think of the twin paradox. The person who stays put moves on a geodesic and ages more than the person who goes away and doesn't move on a geodesic and ages less. So we're talking about a maximum, but in fact, I don't even need to know that because it's really the extremum property that's going to be important for us. Okay, so we're going to do this with the traditional methods of, the calculus of variation. So you've all been through that. I could do it in a very sort of, straightforward pedestrian way by just, working out the Lagrangian and, and doing either plugging that into the Euler-Lagrange equation or doing the variation from scratch. I could do it in all sorts of ways. I decided to do it in a way that's more geometrically satisfying, at least to me. And it allows me to introduce a structure here that I'm going to be able to recycle for other purposes. And in fact, it's the same sort of structure that I introduced when I was talking about Lie derivatives. So some of this will sound pretty familiar. But what's the idea is that, well, we're going to have a functional that's going to be the proper time functional. And we're going to be evaluating on some reference curve. And then we're going to be evaluating on a whole bunch of neighboring curves that are going to be variations of the reference curve. And then we're going to look for the point where the functional is, an extremum point like this. So familiar ideas, I think, from the calculus of variation. So here's a reference curve. That's the one that eventually will be identified as the geodesic. And to do a variation, what I'm going to do here is to introduce a whole bunch of variations on that curve. The only requirement is that they have to start and end at exactly the same point. Other than that, they don't have to do anything at all. They can be completely arbitrary. So we have a reference curve, and then we have a whole bunch of variations of that curve. And we're going to introduce those curves in a way that's familiar, I think, from last week. We're going to parameterize those curves. Those are going to be parameterized curves. And we're going to have 2 parameters. One is going to be a parameter that we follow if we move on a given curve. And then there's going to be another parameter that will tell us if we're on that reference curve or some of the other variation curves. So it's going to be a two-parameter family of curves. So the parameter that's going to be running up the curve, I'm going to call t. And that's just an arbitrary parameterization of the curve. And then the thing that distinguishes the reference curve from the other ones is that the reference curve is going to have a label that we're going to call epsilon, and it's going to be 0 on the reference curve. And it's going to be something else on any one of those variation curves. So we have a two-parameter family of curves. And this will be described to us by functions of those two parameters, t and epsilon. And the idea is that, well, if we let t vary and epsilon stays fixed, then that means that we're either on one of those on the reference curve or any one of those variation curves. We're moving along one of those curves by letting t go up and keeping epsilon fixed, because epsilon is going to be the thing that labels each one of those curves. So that would be a motion along each curve, either reference or variation. But then if we let epsilon vary and we keep t fixed, then that means that we're going from one point with a value of t here to a similar point with the same value of t here on neighboring curves. So we're describing motions across those curves. So two parameters, one that takes us up along each one of those curves, and then the other parameter that takes us from one, so across curves. So moving like this from constant t to constant t to constant t on each one of those curves that we can find in that two-parameter family. So that's the kind of construction that I'll be starting with, and then we'll just extract the consequences of this and then find a way to do the variational principle in a way that at least pleases me, hopefully will please you as well. Now, in case this looks a bit mysterious, what, in typical textbooks, presentations of this, what typically will be done here is to expand that function of epsilon in powers of epsilon, and typically we would stop at first order because we're going to be looking at small deviations from the reference curve. So if we were to do this, that would be the description of the reference curve, and that would be the deviations away from the curve. That's typically how you would set it up in a variational calculus. All I'm saying here is that, well, I could do this, but I don't have to do it. I could just leave it at that without even thinking of doing this Taylor expansion. I will do a Taylor expansion, but that will occur at a slightly later stage. But just to make sure that you don't get lost immediately here, that's what we could have done, and we just choose not to do it, until a little bit later. So we're good so far? So this construction here, where we have a two-parameter family of curves, that's a construction that will come back. We'll talk, we'll use it to do other things. Okay, so I have two types of motions, one along each curve, and I have motions across curves. And because we have those, this family of crisscrossing curves, we also have the tangent vectors associated with them. So a vector that takes me up along the curve, that's tangent to the curve, I'll call t. And that's going to be what happens when we take these functions here and we differentiate with respect to t. That derivative will define for us a tangent vector t along each curve. And then we have a different tangent vector that corresponds to the other way of moving in that construction. I'll I'll redo this, I think, do it better. So we have the reference curve, we have neighboring curves, we have motion along the curve that gives us a tangent vector t, and then we have motion across the curves, and that gives us a tangent vector epsilon. And that's what happens when we keep t fixed and vary the epsilon label. So all I'm trying to say here is that corresponding to this motion, we have a tangent vector that's going to be called t alpha, and that by definition is going to be the partial derivative of those functions over here, where t is varied, but epsilon is kept fixed. So that means that we move up in t, and we keep epsilon fixed. That means that we're staying on any one of those given curves, and that defines the tangent vector t. So that is given to us by the construction. And then for this type of motion over here, we have a different tangent vector. I'll call it epsilon. I think the notation is suggestive here. And that corresponds to, varying epsilon, keeping t fixed. So that's when we move at constant t across curves by changing epsilon. All right, so I'm taking the time to set this up properly because I like the geometrical aspects of all of this. But we'll get to the bottom, we'll get to the crux of that in just a few seconds. But so I hope everything is clear and straightforward at this stage. Okay. So let me specify one more thing. So we have defined those tangent vectors. What I want to do now is to, let's see, I want to keep that board, so I'll go away here. Keep that equation because we'll use it in just a second. Okay, so before we get started with the real thing, I want to show that the Lie derivative of the t vector with respect to the epsilon vector is 0. And because the Lie derivative is antisymmetric when we're talking about vectors, this is also saying that the Lie derivative of the epsilon vector with respect to the t vector is also 0. So I want to show this, and as a consequence of this, we'll have that this derivative, namely t covariantly differentiated in the direction of epsilon, that's equal to the t derivative of the vector epsilon. So that's the property that I'm going to use in my variational calculation. And to prove this, well, we can just see what's implicated in that Lie derivative equation. So that's why I wanted to preserve this. So if I want to calculate the Lie derivative, let me write it for epsilon and t. Then if I'm not invoking the, so if I use the raw form here, what I'm dealing with here is the partial derivative of t with respect to epsilon in the direction of epsilon minus the derivative of the epsilon vector in the direction of t. So here I'm going back to the partial derivative statement of the Lie derivative. Over there I was using the covariant derivative statement because, as we talked about, we can always go back and forth between those ways of writing things. But I'll prove that this is 0 by just working out what the right-hand side is. And in fact, I think you're going to see what it is because that partial derivative here is where I take a partial derivative with respect to the coordinates, and then I project it in the direction of the epsilon vector. And that turns those partial derivatives into a derivative with respect to epsilon. So that first term here, literally, is a partial derivative of my t vector with respect to the parameter epsilon. Yep?
Is it always the case when we have this lit derivative on one vector with respect to the other vanishing? That means we can write them in the form of this, with this x alpha, for example?
In this form?
So yeah, so from the fact that t equals dx of t and epsilon equals dx of the epsilon follows that. So the converse.
Yeah. So you're going to see it straight away, right? Because I'm defining those vectors as partial derivatives with respect to two different parameters. The second order derivatives will commute, and that's what gives me the vanishingly derivative. So that's where I'm going with that.
Right. And the other way around doesn't work. So say I have the 0, does it mean that I always can write t as
I think so, yeah. I think you can always introduce a parameterization where if that's given to you, you can build those vectors in that way. Okay. So yeah, I think it works both ways, but here we'll just work it through this way. All right, so let me complete this because maybe not everybody saw where we were going with this. So here I'm defining the epsilon derivative of t alpha. Here, by the same reasoning, I'm talking about the t derivative of the epsilon vector. Because what am I doing here? I take derivatives with respect to all the coordinates, then multiply by t beta. But t beta is just derivatives of the coordinates with respect to t. So apply the chain rule of differential calculus, and that defines a partial t derivative. So we have that. But then we can use those relations again. Here I have the epsilon derivative of the t derivative, and here I have the t derivative of the epsilon derivative. So I'm talking about two partial derivatives of the same functions in two different orders, and then we know that it doesn't matter in which order you take that, so you get 0. So given the construction, given the definition of the tangent vectors, it was guaranteed that those vectors were Lie differentiated along each other, and that allows me to write this statement over here that we'll actually use in the calculation, but something which by itself may not have looked completely obvious. All right, are we all good with this little calculation here? Okay, I'll take that as a yes. Okay. Well, now let me get started. Have done nothing so far, so let's get us started. So now I'm going to introduce the proper time functional, and we're going to look to extremize it. Okay, let me just specify one more condition. So we have a lot of freedom in choosing the parameterization of those curves, just for concreteness and also for technical ease in the calculation. I'm going to choose all the curves to start with one value of t and end with the same value of t. So I'm going to say that for all curves, reference and variations, we're going to say that t at p is going to be some specific value, might as well take it to be 0, and then t at q is going to be some specific value 1. So the point here is that I want those n values for the parameter t to be independent of epsilon. And here we can always arrange the parameterization to achieve this. It's just a matter of making sure that all those curves start here at t equals 0 and end up there at q at t equals 1. So we can always, here the parameterization is completely arbitrary, so I can always achieve that. Yep.
In that result, did we just use that the derivative should commute and it will cancel and give us 0? Or are those like separately 0 because we defined like T alpha as in constant epsilon and epsilon alpha and constant T?
Can you repeat? I'm not sure I got the question.
So these terms, are those separately 0 or is it just like...
Oh, no. No, they're not separately 0, but because two partial derivatives commute.
Yeah, I was confused that because we define T alpha, for example, in a single epsilon, right? Like
yeah, no, that's something that tends to confuse me as well. So here I said take a T derivative while keeping epsilon fixed, but after that you can take an epsilon derivative.
Which is not 0.
No, that's right. So we're allowed after the fact to reintroduce epsilon as a varying parameter. It's just that here I wanted to be very explicit about, the meaning of partial, meaning you differentiate with respect to one, keeping the other one constant. But yeah, I mean, that tends to confuse me as well sometimes. I mean, I have to keep reminding me that, okay, I did it momentarily here, keep epsilon to be constant, but after that I still have a function of epsilon that can be differentiated with respect to that, right? And same story here. Yeah, thank you for clarifying that, or, yeah, so it's important. Okay, so let me reintroduce the diagram here, and I'll just talk about the reference curve for now. So we have Q, we have P. And what I want to do here is to use the interval of proper time between those 2 points as my action. So the proper time, well, how do we define proper time? Well, proper time is defined like ds squared. We call it d tau squared, but it's just minus ds squared, and it's just minus the metric multiplying the displacement along the curve. So without without a minus sign, we would call it proper distance, and that would be appropriate for a space like geodesic. Here, because I'm focusing on time like geodesic, I want to use proper time, and there's that minus sign difference. So I can take the square root and get the infinitesimal of proper time on the curve. And because I'm doing this with parameterized curves, I can introduce the parameter at this stage. So what I'll do here is inside the square root, I will divide the coordinate increments by the parameter increment, and then I'll compensate by multiplying by dt, so that at the end of the day, my infinitesimal of proper time along the curve I can express as this in terms of the t vector, because it's understood here that when I'm differentiating with t, I'm keeping, I move along one of those curves, either the reference curve or any of the variation curves, but that's understood that we're keeping epsilon fixed when we take this derivative, so it's really a partial with respect to t, and therefore it's really the same thing as the tangent vector t alpha. All right, and then, to define the interval of proper time between p and q, all we have to do is to integrate this and that is almost what I want to pick as my action functional. The other thing that I'm going to do is to introduce an overall minus sign for reasons that maybe you'll appreciate a little bit later. But the way I'm going to motivate it now is to simply to say that, well, we're looking at an extremum, but we're really thinking of this as being a maximum. If I introduce a minus sign in front of this, I'm going to change the maximum into a minimum, and maybe we feel better about that. It's a flimsy argument, but, I'll take it. I'm going to show you later why I want to have an overall minus sign. It doesn't change anything about the calculation, except that at some point, something will make more sense. So that's my ulterior motive, so keep that in mind. So what's my action functional? Well, it's going to be minus that integral, and now I'm going to specify that for all the curves we're integrating t between 0 and 1. So that's the thing that I want to extremize. And, at this point, after a lot of setup, I could do the usual variation. We have a metric that depends on the coordinates. Those would be the generalized velocities. I could plug that into the Euler-Lagrange equations. And, with a bit of a laborious calculation, I would get out the geodesic equation. So we could proceed this way. That would be the pedestrian approach, and that's what I do in the book. But now I'm older, wiser, I can do better than this. So I want to really exploit the geometry of the situation, this Lie derivative business that we talked about, and turn what could be a laborious and boring calculation into something magical that you'll go, wow, it's so great. I'm always hoping for that kind of reaction. I never get it, but that's a different matter. Okay, so now we're ready to actually get started with this. Okay, so let me go up here. You've lost out. Okay, so I'm going to do the variation from scratch. I'm not going to rely on the Euler-Lagrange equations. I'm just going to do the variation from scratch, and I promise you it's going to be very nice. Okay, so what do we mean by taking a variation of the action? Well, what we mean is, we have the reference curve. We're going to evaluate the action on that curve, and then we're going to pick any one of those variation curves. We're going to evaluate the action on that curve, and then we're going to take the difference. And at the end of the day, we're going to, look for an extremum point, which means that that difference will have to vanish. So that's the usual story. Mathematically, what this means is that we're going to evaluate the action for one non-zero value of epsilon. Now we're going to think of this as being small. And we're going to compare that to the value at 0. That's the value at the reference curve. And we're going to be looking for an extremum point, which means that we're going to be looking for the conditions that make that ds vanish to first order in epsilon. That's the usual setup in the calculus of variation. And this translates into taking an epsilon derivative of the action. And, if I should have introduced some more notation to simplify the steps here. I'm going to say that the Lagrangian corresponding to this action is going to be minus the square root that we have inside the integral. So I'll be thinking of that as the Lagrangian, including the minus sign. Okay, so what does it mean to take an epsilon? Okay, so I take this epsilon derivative, and then I evaluate the derivative at epsilon equal to 0. And what does it mean? Well, it means that what we're going to do is take an epsilon derivative of the Lagrangian. And we're going to be working on this, and we're going to be demanding at the end of the day that this first order variation of the action vanishes. And we're going to make all the usual stipulations. We want all the curves to start at the same point, blah, blah, blah. Okay, so we have to work on this. So what does it mean to take an an epsilon derivative of L? Well, that means, as it meant before, that we're going to be calculating a derivative in the direction of the vector epsilon. So I'm going to interpret it like this, because that's what it is. And I can write it in terms of a partial derivative, or I can write it in terms of a covariant derivative, because L is a scalar, it makes no difference. But I'm going to write it as a covariant derivative, because that scalar L is made up of two ingredients, the metric and the tangent vector t, and those are tensors or vectors, and there the covariant derivative notation will matter. I'm going to run into trouble with indices here, so I'll change the identity of those indices before I go too far. Okay, so how do I calculate that derivative of L? Well, L depends on two things. It depends on the metric, and it depends on t. So I'm going to take a derivative with respect to each, and then apply the chain rule. So first I have the epsilon vector, and then to take this derivative, the first thing I'm going to do is to take a partial derivative of L with respect to the metric, which, we can calculate if we wanted to. And then, applying the chain rule, I'm going to take the covariant derivative of the metric. And then we realize that we don't have to do anything here because that covariant derivative is 0. And then I would take the partial derivative of the Lagrangian with respect to the tangent vector and take its covariant derivative its covariant derivative. So that's the calculation that we have to do, and that goes away, and we're left with this. So what are we left with? We're left with partial L, partial T, with respect to alpha, and then we have epsilon covariant derivative of t. And now I'm going to make the switch. That's why I needed all of this, because I want to switch this derivative for the other derivative. So that's the derivative of t in the direction of epsilon. That's this one. I want to make the switch to that one. That's going to be the t derivative of epsilon. So that's why I needed all of this, because I wanted to make this switch first. It's a bit annoying to carry this all the time, so I'm going to come up with notation. So that vector here that I get after differentiating the Lagrangian with respect to the generalized velocity, well, that's the generalized momentum. So let me introduce the standard notation for momentum. I'll call this, just give me a second. I'll call this P alpha by definition. That's a generalized momentum. And this I'm going to say we're going to replace by the t derivative of the epsilon vector. Somebody had a question?
Yeah,
yep.
could you explain how you got the function covariant derivative to the right hand side? Like, I guess you're saying that the Lagrangian only depends on t and t. That's why we can break up the covariant derivative.
Right. So I can take the Lagrangian to be a function of the metric and the tangent vector. So if I want to differentiate this with respect to anything, I have to partial with this, differentiate that with respect to the coordinate, and then do the same thing here. And the only thing that I did on top of that was to, instead of doing it with partials, I could have done it with partials, but then we would have to contend with partial g, which is nasty, because it would have to be re-expressed in terms of Christophel's tensors. We would have partial t here. We would reconcile all of this eventually, because we would see that all those Christoffel symbols that arise here would make up this covariant derivative. So it's easier to do it from the start with the covariant derivative, apply the chain rule with the covariant derivative, and immediately we can set that to 0 and get this at the end. Yep.
And we should, this might be a dumb question, but how do we know that derivative is 0?
You review last week's lecture.
Okay.
Yeah. Other questions?
How can you take the partial derivative to covariant?
Well, because here we're acting on a scalar. So covariant and partial on a scalar is the same thing. But how I interpret the derivative when I break down, the dependence in terms of g and the dependence in terms of t, because those are tensors, it's advantageous to introduce from the start the covariant version of that calculation. Yep.
How do you know for certain that the chain rule works this way for covariant derivatives? Is this something you derive separately, or?
Yeah, you could derive that for yourself. So two options here. You could redo this calculation with partials, where maybe you're on safer grounds, and then see how all of those partials, G's, would combine into Christoffel symbols, and eventually would give rise to that covariant derivative, I mean the one that lives here. Or just do something more general and just work, derive the chain rule where you go from partial to covariant and make sure that all the gammas take care of themselves. So my promise to you is that it will all take care of itself.
Oh, that's a universal thing all the time.
Yep. Yep. Chain rule applies to any kind of derivative operator. It doesn't matter whether it's partial, covariant, Lie. It's pretty much guaranteed to. I think it is guaranteed to work for anything like this. As long as the Leibniz property is satisfied, you're all good to go. Other questions?
Oh, I guess so. If supposing that L, G, and T are just arbitrary tensors, this relation always holds.
Which relation?
That you can really go with covariant derivative.
Oh yeah. So here I could have a really long list of dependencies, including all sorts of tensors, and then the idea would be partial with respect to each independent ingredient, and then apply the chain rule to that. Yep. All right, all good to go? Okay, so we've done a few things here. So just to make this more obvious, so I've defined the momentum associated with my dynamical variables here by doing what we always do, take a derivative of the Lagrangian with respect to the generalized velocities. So I'm introducing this notation here, and then I've made the switch. And then what I have, for the partial derivative of the Lagrangian with respect to epsilon is P alpha, then T mu covariant derivative of the epsilon vector. And this I'll write it in a slightly more suggestive way. So we're taking the epsilon vector, the one that takes us across all the curves, and we're taking a t derivative of this, but it's a t covariant derivative. And because we're differentiating along the direction of the t vector, we're moving up the curve. So that's really just the covariant derivative of the epsilon vector with respect to the parameter t going up the curve. And when I write it like this, I think it becomes very suggestive, because obviously the first thing I'm going to do here is to integrate this by parts, and then we'll be done, almost. Okay, so let's keep going with this. I'm going to plug that inside my variation of the action. So I'm going to kill that factor of epsilon that I don't really need anyway. So 1 over epsilon times the variation of the action, that's going to be to us the integral between 0 and 1 of what we now got. And now I have to work on this, but we're one step away from being done, basically. I'll just pause here and just tell you that the reason why I like this approach better is because, first of all, there's some nice geometry that goes into it. But more pragmatically, when you do the variation in a pragmatic way, you end up having to differentiate the metric with a partial derivative. And that always generates a mess. That's how you have to reconstruct the Christoffel symbols that eventually will give you covariant derivatives that will show up in the geodesic equation. And that step is not that difficult, but it's a bit nasty and it's a bit unpleasant. And here I'm bypassing all of this by, doing all of this. So that's where you're supposed to go. Aha, so much better. Okay, so let's rewrite this as a total derivative minus the swap derivatives. And here I'm taking the covariant derivative of a scalar up the curve, so that's going to be the same thing as an ordinary derivative. So that's a total derivative I can integrate, and I'm going to be left with this inside the integral. So the final expression for the variation of the action is going to be the scalar product between p and alpha evaluated at the boundary points minus an integral of epsilon alpha dp dt integrated on the curve. And now we're done. What's the next step is to say that we're doing variations with, two important characteristics. We want the deviation vector between all of those curves to go to 0 at the endpoints. We want all the curves to begin and end at the same points. That means that the epsilon vector that measures the deviation from the reference curve, that's got to vanish at the endpoints. So we're going to kill that. But the curves in between the endpoints are completely arbitrary, so that deviation vector here is completely arbitrary. So we have an integral that involves an arbitrary factor times something else guaranteed to be 0 when we take the variation to be 0, and that gives us the statement that this by itself has to be 0, and that, in disguise, is the geodesic equation. So the last step is where it all comes together. So first we spell out the rules of variation. And that means that epsilon is arbitrary between P and Q, but 0 at P and Q. So that's what we mean. We want to consider an arbitrary variation of the reference curve, but we insist that all the curves begin and end at the same points. So that allows us to kill that at the boundary points. And the fact that, and then, we demand that ds be 0, that means that the integral has to vanish for an arbitrary epsilon. And the only way that this can happen, if we insist that epsilon is arbitrary, is for the thing itself that we're trying to integrate to be 0. So that means that at the end of the variational calculus, we get that statement, which, perhaps in disguised form, but we'll make it more explicit in just a moment, is the statement of the geodesic equation. It's the statement that if the curve satisfies this equation, it will give us an extremum of proper time between two fixed points. So we still have to, unravel some of this, but that's the main conclusion, that we end up with a very neat, looking expression or statement of the geodesic equation, and all we have to do now is to, unravel this with the notation we introduced for the momentum vector. Like that. Okay, so we're good? Okay, so that's, those are the Euler-Lagrange equations that must be satisfied for the curve for the statement to be true. And now we can unravel this a bit and see what it really means. Okay, so let me write the Lagrangian as minus, minus. I'll rename the indices here so I don't get into trouble. So that's the thing that we have to differentiate with respect to T alpha to define the momentum. So what do we get? So we differentiate, so I'll just carry out the differentiation. So we're calculating this, which means that, well, I have to multiply. So there's a factor of 1/2 that's going to come down. There's a factor of this that's going to come down as well with, we get 1 over that square root. And then we have to differentiate this with respect to T, thinking of G as being something fixed along this calculation. So we're going to get minus G. I forgot this minus sign, so it has to come out too. So we get this minus G, and then I have to differentiate this product with respect to T alpha, so I'll just carry out the steps here very slowly to make sure I don't lose anybody along the way. So sorry, I'm getting lost with my indices. So this is T mu, dt mu, dt alpha. So that's what we do when we take the partial derivative. And this over here means that I take each component of the t vector and differentiate it with respect to each component of the t vector. And all those components are independent. So I only get something non-zero when mu matches alpha. So that gives me a Kronecker delta. That gives me another Kronecker delta, because all of those components are independent, and I'm differentiating each one with respect to each one. So I only get a non-zero result when I differentiate T0 with respect to T0, for example. And now I can rewrite all of this. So I have two minus signs. They kill each other off. I'm going to get 1/2. This is a factor of 1 over the Lagrangian, so I'm going to sorry, this is minus the Lagrangian. So now I can see that maybe my sign conventions were not. Anyway, doesn't matter. I'll write it like this. 1 over minus the Lagrangian. And then I have G mu nu. But I'm going to do the summation over the repeated indices here. So first I kill the minus sign. I'm going to get G alpha nu T nu. And then for the second term, I'm going to get G mu alpha T mu. And I hope you can see here that I'm just lowering the index in both cases, and I get twice the same thing. So in the end, my p vector, my momentum vector, is going to be, I kill the 1/2 because I have twice the same thing. I get 1 over minus L times the lowered version of the tangent vector. Right. Or I could raise the indices on both sides, and then I would get 1 over minus L T alpha. And just as a reminder, my L was actually negative, right? So minus L is a positive. So I just have a rescaled version of the tangent vector in the momentum vector. Still with me? Okay, so now we can see what this means in terms of the geodesic equation.
Can I have a question?
Sorry? Oh, yeah, yeah.
Can I have a question?
There's someone online. Sorry, I didn't know you were there. Yeah, please do.
For null geodesic, what we ought to do, because L is 0.
That's right. So null geodesics are problematic. So I'm not going to do anything until I talk properly about null geodesics, and that's going to have to wait a few weeks. So for now, I will say that null geodesics are excluded from this analysis. We're restricted to time-like, or there's a space-like version of this that's very similar to that. And we can think of null geodesics at the end as emerging as a limiting case. But I'm going to do a much more thorough discussion of null geodesics in due course. So stay tuned for that. Thank you for the question.
Okay, thank you.
Okay, so now we're almost there. So where's my statement of the geodesic equation? I've lost, oh, it's over there. I can rewrite it with the index up because I can again invoke the metric and plug that into the covariant derivative, and that doesn't do anything. So I can rewrite the geodesic equation in this form. But now that means that what I have to do is to take the t derivative, covariant derivative, of the t vector divided by minus L. Would be very convenient if minus L turned out to be a constant. Then we wouldn't have to work so hard. And I'm going to take that step in a moment, but not just yet, because I want to make a point about this. So let's take the derivative. So first we have the factor of minus L that doesn't get differentiated. So we're going to get the covariant derivative of the tangent vector with respect to t. And that's something we could interpret as the acceleration of the curve, right? And then I have to differentiate the minus L. So here I'm going to minus L squared, and then I have to take the derivative of minus L with respect to t, and that multiplies t alpha. So I get two terms. And if I put that to 0 and I kill one of those factors of minus L, I'm going to get d covariant derivative of the t vector, the tangent vector to the curve. That has to be equal to, I'll write it as 1 over minus L derivative of minus L with respect to t, multiplying t alpha. So that's sort of clumsy notation. I'll just introduce the standard notation for this. I'll call this kappa. And what we're getting here is that the geodesic equation at the end of the day has a formulation that may look a little bit surprising. We're not saying that the covariant derivative of the tangent vector is 0 along the curve. We're saying it's actually something proportional to itself, to the tangent vector. And the reason why we're not getting the familiar equation with the 0 right-hand side is because I've chosen my parameterization, t, to be arbitrary. And if we do that, and sometimes there are good reasons to do that, we don't get a 0 right-hand side. We get something that involves that additional quantity here that corresponds to the t derivative of minus L. So we get something a little bit more general. And sometimes, as I said, there are very good reasons to be that general. There are good reasons to introduce a parameterization that's not restricted to proper time. But if at the end of the day we choose to simplify our lives by choosing proper time as the parameter t, then we can simplify this, and that's going to be my last step before we break for today's lecture. If we choose a very specific parameterization after we're done with this variation calculation, so after variation, we can choose t to be proper time, tau. We can pick that way of parameterizing the curve, and that guarantees that our Lagrangian is in fact going to be equal to -1. Because what's our Lagrangian? Do I have it anywhere? Well, the Lagrangian was minus the square root of now this version of the tangent vector where we specifically choose proper time as the parameter. And what do we get? We get minus the square root of d tau squared divided by d tau squared. So sure enough, it's equal to -1. So by choosing that very specific parameterization, we make L a constant, and that means that we make kappa 0, and in that situation, we get that the geodesic equation becomes the more familiar equation in terms of proper time. So that's a specialized variation. So that's also the geodesic equation, but with proper time parameterization. And that's when it takes the familiar simple form, whereas if we insist that the parameterization should be general and we reserve the freedom to specify it in a way that may not be a proper time parameterization, then we end up with something that looks a bit more general. So the reason why I wanted this is that at some point this will resurface. And especially when we talk about black holes and we talk about the structure of an event horizon, that event horizon is going to be described by a null surface that's going to be traced by null geodesics. It turns out to be very convenient to use a parameterization of those null geodesics that's not going to be an affine parameterization or parameterization that would be analogous to a proper time parameterization, except that we're talking about null geodesics. Instead, it's very useful to use a more general parameterization with a non-zero right-hand side like this. So you didn't have to follow this little bit of discussion, but the point is that I wanted this to be established before I reintroduce it, and it's going to be weeks from now, so you'll have forgotten, but I'm going to tell you, remember, when we were talking about this, now it's going to be playing a role. Okay, so I think that's enough for this morning. Any questions before we break? Good. Any questions online?
Thank you.
Okay, very good. So I'll see you in the afternoon.